In this video, we're going to talk about vectors. But before we actually do, let's look at why we might need them. Recall that one of the most important ideas in calculus is derivatives, or in other words, the concept of slope. We care about slope a lot because it tells us something about direction. So various slopes give us different directions. So if we're working in our xy plane, so each of these different lines has a different slope. Maybe we might move the lines around and have them not exactly the same line. So we have something like this that has the same slope as something like that. But the direction that they're going in is the thing that's kind of important, and that's what the slope is telling us. Technically, we do have the direction of no slope, the vertical direction, but that still gives us an idea of what's going on. Unfortunately, when we talk about three dimensions, there's a lot of directions. And it's not very easy to refer to each direction by a single number like we could do with slope. And so that's why we bring in vectors. Essentially, we're going to make objects that have a direction as part of the information that's involved here. Though we actually go a little bit further, and we say that a vector, or at least informally, we'll not get into the more formal definition what vector means here, but for us here, it's going to be something that has a magnitude, or in other words, what we might say is a length, and a direction. And for the moment, we're just going to leave it that vague. We'll get into how we can actually work with that as we go through this video. So normally, and we can do this in both 2 and 3 dimensions. If unless I need the 3 dimensions, I'm just going to draw 2-dimensional pictures. They'll make it a little easier to work with. But generally, what we'll be doing is just drawing a vector as an arrow. Or you can even think of a vector as an arrow if we prefer. But it's something that starts somewhere, goes a certain distance, and ends somewhere. We can say this is the vector from point A to point B if we prefer. A is going to be called our initial point. Why did I put a parentheses there? So our initial point. B is our terminal point. And we do care about whether it goes from A to B instead of going from B to A. Going from B to A would be a different vector. Now, there's a number of ways we can actually denote these. If we do have 2 points in mind, we might say AB with an arrow over it. That's an easy way to do that when we have 2 points here, but usually this is actually a little bit complicated to use in formulas, so a lot of times we'll just go ahead and give those a name. So we'll call this vector v, just like x is our normal variable for numbers. V is frequently our normal variable for vectors. And usually when vectors are done in, say, books or print, we'll have a boldface character. That's a little bit more complicated to do in writing, or when I'm just doing it here. So instead of boldface, sometimes people just go ahead and put an arrow over it like we did with the AB. Or if there's no risk for confusion, I'll just go ahead and put the letter V, just because it's a lot simpler to do that quickly. But the point here is that if we're going to have, say, a vector v and a number v, we want to go ahead and put the arrow over a v if we're talking about the vector. So if there's any risk of confusion, we'll do that. But I'll probably be sticking with just the letters as they are most of the time. One thing to note about vectors is that we don't care where they start from. So here I picked my initial point A. I could have said instead pick the point C. And as long as I keep that same length, that same magnitude, and that same direction, I could be talking about this here. This might still be the vector v as long as the length and the direction are the same. So these are should be parallel lines. Hopefully I made them parallel enough, and hopefully I made these the length of these the same. But these are the same vector. We can say that these vectors are equivalent or equal, but most of the time we're just going to treat them as the exact same vector. There's not really any difference between these two things. And that's kind of what helps make vectors so useful, is their position isn't too important, but their magnitude and direction are. And that's the kind of concept that we want to be getting across. Now, of course, in order to do computations with vectors, we're going to want to work with numbers. We want to somehow attach numbers to the vectors so we can actually work with them. Because we know how to add and subtract numbers, it's not so easy to do with vectors as we have them so far. We'll get into what that will mean in a moment. But the key point is going to be the fact that we don't care where they start. If we have our vector, so we had our vector AB from before, if we want to attach numbers to that, let's move it so that the initial point is at a very easy to work with position. Let's say the origin. If we move that to the origin, that's not quite parallel, make it a little bit more sloped. Here we go. Let's say we move this vector so its initial point is at the origin. When we do that, the terminal point will be at a particular place. Let's say AB. We're going to say that this vector v, has components a and b. So here, if the coordinates of the terminal point when the initial point is the origin is AB, then the components are AB. And we'll use angle brackets to when we actually talk about components instead of coordinates. So we'll say this vector v, we'll even just say v equals angle bracket A, B, angle bracket. Or if we're working in 3 dimensions and we have 3 coordinates, we'd have, say, A, B, C in that case. A lot of the times, if we're just talking about a vector v, we might name its components as v1, v2. Just use the letter that we're using for the vector, and then attach numbers as subscripts so we can actually easily to identify what vector we're working with or which vector the components came from, especially if we're using more than one vector at a time. But the point here is that we can easily turn this into just a collection of numbers, and those numbers tell us exactly what vector we're working with. We can also use these components to tell us what the magnitude is. So here, because we're talking about the distance from the origin to this point, that's our magnitude, which we usually will go ahead and write as kind of the absolute value of the vector, or sometimes you can say a double absolute value. I think the book uses the first one, but the second one is in pretty common usage as well. But here, we're just saying, we'll go ahead and use the v1, v2 notation. We have the square root of v1 squared plus v2 squared. Once we have the components, the magnitude easily comes from those components. This is basically just the distance formula of the Pythagorean theorem that we talked about in the last video. Of course, direction is a little bit more complicated. Mostly because of what we talked about before. In 3 dimensions, we don't really have an easy way to even talk about what the direction is without vectors. So we'll just normally just work with the components as we have them so far. If you do care, in section 12.3 in the book, it does talk about direction angles that you can actually talk about, but I don't really see any reason to talk about direction angles instead of just working with the vectors. So we'll just stick with vectors. In 2 dimensions, we can talk about the slope. The slope as being our concept of direction. And here, just keep in mind what we're doing here. We're going from 0 to AB, or 0 to V1, V2 if you prefer. And so the slope is just going to be our difference in y's, which is the V1, over the difference in x's, which is our V2. That's what the slope is. Now, if we don't start with a vector at the origin, if we have a vector going from A to B, we can actually get the components pretty easily. So here, just to draw a picture going with this, let's say we have point A here with the coordinates x1, y1, z1. We have point B over here with coordinates x2, y2, z2. We're talking about the vector going from A to B, and I guess they're calling this one A, a capital A. The components of the vector from A to B is given by subtracting our x values, subtracting our y values, and subtracting our z values. It's just that simple. We take the terminal point, the coordinates of the terminal point minus the coordinates of the initial point. And it is in that order. We're not going to take x1 minus x2. It's specifically x2 minus x1. If we do the other order, we get the vector from B to A instead. But if we use this formula, you can kind of see that what these formulas up here for magnitude and slope are really just boil down to the distance formula. And especially in the case of slope, remember V1 here is x2 minus x2. Sorry. Why did... Okay, sorry. I messed up here, didn't I? I don't know why I put those in the order that I need them. So the difference in y's is v2. The difference in x's is v1. Sorry for confusion there. V2 is the difference in our y's. So this is y2 minus y1. V1 is the difference in our x's. So this is x2 minus x1, and this just becomes our normal slope formula. The normal definition of what slope is. So really all the formulas I have written here are the distance formula and the slope definition. But the point here is that we've now developed a way to talk about these things in 3 dimensions, and that's the important thing. Now, vectors wouldn't be that important unless we can do stuff with them. So we are going to talk about various operations we can do with vectors. The first one is addition. So let's say we have 2 vectors. I'm going to leave off the coordinate systems for now. Let's say we have a vector u and a vector v, and I want to add these two together. How do I add these 2 arrows together? What do I get? Well, the idea is that we are going to kind of stack them on top of each other. We're going to start with u and follow it by v. So imagine we're starting somewhere. We're sitting here somewhere. We follow the vector u. That means we pick a direction, the direction of u, and we go the distance that u travels. So we follow u. Once we follow u, we end up at a point. That's going to be our new starting point for following v. So v goes off in this direction. Kind of got that a little off, but oh well. And we go whatever the length of v is. So we end up with a point there. So we've started here, we followed u and followed v, and we ended up here. That gives us a new vector. We've gone overall, we've gone a particular direction and a particular distance. This will be the vector u plus v. The book refers to this process as the triangle law, because what we get here is a triangle. Now, if we want to, we could add more than two vectors together. We could add 3 or 4, 50 if we wanted to, and it'd just be a matter of just follow each one in turn, and you end up wherever you end up after you follow all 50 of them. That At that point, it doesn't really look like a triangle, and even with two vectors, it might not look like a triangle. If those vectors are, say, in the same direction, it may look very different. But the point here is not the triangle shape, it's the idea of just stacking them one after another. Another way people like to do this is, instead of looking at a triangle, think about putting the two vectors u and v starting from the same point. So let's say we have u and v here, and instead of like moving v over to the end of u, we'll kind of think about this as the beginning of a parallelogram. So we make another line that's parallel to u, another line that's parallel to v, and we end up with a point over here, and the diagonal from that same starting point to this intersection point over here, that's going to be our u plus v. This is what they are calling the parallelogram law. Now, my picture looks more like a rectangle. They don't have to be perpendicular to each other. They could be a little bit more elongated. But really what's going on here is that this line up here is just another copy of u. If we think about going from here to this point here, that is just of the vector u. Same thing with over here, we actually do have a vector v, another copy of v. And so really this is just two copies of the triangle law. But the main thing to note here is that this actually shows us a certain property of addition. When we follow u and then follow v, we get the exact same result as if we follow v and then u. Basically, u plus v is equal to v plus u. The order doesn't matter here. It's a little harder to see that that's true in general. If we talk about more than just two vectors, this will be true that we can change the order however we want to, and we get the same result. We'll talk about more about the properties of this in a little bit, in a few pages, let's just say. Alright, the next operation that we're going to talk about is what we call scalar multiplication. So we're not going to be multiplying two vectors, so we're not just going to call this multiplication. When we talk about vectors, a lot of times people will refer to just regular numbers as scalars. So think of scalars just meaning number. So 2 is a scalar, 3 is a scalar, pi is a scalar. Anything that's just a regular real number is going to be a scalar. Technically, you could even have complex numbers as scalars if you want to. We are not going to do that here at all. So don't worry about that. So when you hear scalar in this class, think a real number. And what scalar multiplication is going to do is we're going to take a vector times a scalar, and we're going to get a new vector out. So take scalar times a vector, and that gives us a vector. So let's say we have let's keep that same u from before. I think I made it a little bit longer, but whatever. So we're going to have the vector u, and let's say we want to talk about a new vector 2 times u. Well, 2 times u is going to be the vector that keeps the same direction as u, but modifies its magnitude. And really that's all that we want to do with scalar multiplication, is modify the magnitude. So we're going to take u and we're going to make a magnitude twice as long. So here The direction is exactly the same, but the length is twice as long. So you can even say here that the magnitude of 2u is 2 times the magnitude of u. And that's the whole point. But the direction doesn't change. Now, I'm kind of lying here. Not all scalar multiplication is going to leave the direction alone. If we use negative numbers, we're going to, instead of keeping the same direction, we are going to swap it to the opposite direction. So we could say negative 2u will be parallel to u. In fact, it'll look very similar there until we put the arrow as going the opposite way. So here, the magnitude of negative 2u is actually still twice the magnitude of u, but now the direction is the opposite of the direction of u. But the main point here is that we're kind of still working with the same slope, in a sense, but we've just gone the opposite direction. And in a way, vectors have a little bit more information than slopes already had in the first place, because they actually tell you a particular way to go along that slope instead of just saying, well, we have a line that has a particular slope. We're saying a line and we're going one way along the line or the other way along the line. But really, all that means is that we're attaching a negative if we change which direction along the line that we're going. Now, of course, we define these two operations very geometrically. And it might seem like that makes them really hard to actually work with. But it turns out that when we work in components, we get really easy formulas. So here we have 2 dimensions and 3 dimensions. We'll talk about both of them. So first we have two vectors, a, b. A has components a1, a2. B has components b1, b2. C is actually going to be a scalar, so it's going to be some number. And it turns out if we add two vectors, we end up just adding the x components and the y components separately, and those will be the new components of our vector. We can even do the same with subtraction. Subtraction is something very easy to work with as well. Scalar multiplication, if you multiply a vector by c, it just multiplies the x component and the y component by c, and those are your new components. For three-dimensional vectors, we now, these are very similar, except instead of just going a1, a2, a3, we have a1, instead of a1, a2, we now have a1, a2, a3. Same thing with b. And all we do is we add up the components. We frequently will call this component-wise, meaning that we just do the same thing to each of the components. So we add the x components to get the x component of our sum. For our scalar multiplication, we just end up multiplying each of the components by that scalar. These are very, very simple formulas, and the fact that these agree with the geometry that we define these operations to be is what makes this very useful. And actually, once we have these formulas, that means that we can get various properties of vector addition and scalar multiplication very easily. And it just comes down to just kind of cranking it out using the normal properties that we have of addition and multiplication. So note here that we have a formula we talked about before. So we said that a plus b is b plus a. So the order of the addition doesn't really matter. But we have things like associativity, where if we're adding three vectors together, it doesn't matter what order we add them together in. There is a zero vector. The zero vector is the vector that starts at a point and ends at the same point. So we could say that's zero if we want to. I mean, the zero vector is really the only vector that kind of doesn't have a direction because any direction actually works for it. But it's also the vector just consisting of 0, 0, or 0, 0, 0. It's kind of unique in that sense. We have For any vector, we have a negative vector. And remember, negative, this is basically just -1 times that vector. And if we add a vector to its negative, remember, this would be a, and then negative a would just be the same vector, but going the opposite direction. If we follow that vector and then follow its negative, we get back to the same point. That's what the zero vector means, that we start that at a point, we end at the same point. We have scalar multiplication does work like normal multiplication, where we actually do have a distribution rule, but we actually even have a distribution rule the other way, where the scalars vector can distribute over sum of scalars. It kind of works with multiplication, the normal multiplication of scalars, of numbers, with an associativity rule. And the eighth one here might seem a little bit obvious, but it is kind of an important property if you get into the more abstract ideas behind what vectors are. So here, a vector times 1 is just the vector itself. Most of these are pretty straightforward, but it can be interesting to look at what these mean geometrically. I'll let you guys maybe play around with that, see what the distribution means in a geometrical sense. It might be a little bit weird, in fact, but it is, all this has geometrical meaning. Now, sometimes when we actually do just want to focus on direction instead of including magnitude, because that's really why we're talking about vectors in the first place, is that direction is important. Sometimes the magnitude is not so important, or sometimes it's actually a little bit kind of extraneous and gets in the way. So a lot of times we'll try to just take vectors that have a fixed magnitude of 1. We call that a unit vector. It's a vector with magnitude equal to 1. Given any vector aside from the zero vector, we can get a unit vector with the same direction by just dividing that vector by its magnitude. So if we have any vector v, and we take that vector and we divide by v, by the magnitude of v, so remember this is just the length of v, this is a unit vector in direction of v. And so, in fact, we might say this unit vector is the direction of v. We can say that directions are just unit vectors, and having magnitudes attached to them just gives us more vectors. But of course, this doesn't work if we're talking about v being the zero vector, because the magnitude of the zero vector is 0. We can't divide by 0. Even with vectors, we can't divide by 0. Now, there are a few specific unit vectors that are important. Basically, if we look at our normal coordinate system, and we want to look at unit vectors in the direction of x, y, and z, those are very important directions, of course, because those are our axes. We get unit vectors of what we call them I, j, and k. So I, j, k. These are what we normally refer to as the standard basis vectors. In components, these are very nice and simple. So I is just going to be 1, 0, 0, j is going to be 0, 1, 0, and k is going to be 0, 0, 1. So here, basically, the only thing that we have here for I is the x coordinate, and we go 1 unit in the x direction, but 0 units in the y and z directions, and so on and so forth. Of course, we could do this with 2 dimensions as well. We basically there just have I and j. They're still going to be the directions of x and y, but we don't have that that zero in there, that third component. These are very useful because every vector can actually be written in terms of these vectors. So let's say we have a vector A, which is A1, A2, A3. There's nothing stopping us from splitting this up into pieces. Let's say turn this into the sum of three vectors. Now, it can feel a little weird to be splitting it up, but if we're going to go the other direction, this would be pretty easy. So taking the sum of three vectors, we add the three x values, so a1 plus 0 plus 0 gives us a1, 0 plus a2 plus 0 gives us a2, and 0 plus 0 plus a3 gives us a3. But then I can also pull out the a1, a2, and a3. So remember, with scalar multiplication, a1 times 1, 0, 0 is the same thing as a1, 0, 0. Because we take this a1 multiplied to the 1, the 0, and 0. Of course, a1 times 0 is still 0. And so we can do that. And we can do the same thing with the other two. So our second vector is a2 times 0, 1, 0. And our third vector is a3 times 0, 0, 1. Of course, these three vectors that we have in here are just I, j, and k. This is a1 times I plus a2 times j plus a3 times k. We've taken the vector a and we turn this into what we frequently will refer to as a linear combination of I, j, and k. It's just scalars times those three vectors added together. And that actually is very useful in various contexts. I'll give you an example of that when we get to the cross product. So, main thing to note here is that these are easy vectors to use, but every vector can be written in terms of them. Alright, so I believe this video has gone on quite a while, so I'm going to go ahead and stop there. This is basically the video for section 12.2. I'm going to leave the 12.3 and 12.4 to be its own video. We're basically going to talk about how we can actually take two vectors and multiply them instead of just a vector and a scalar. But I'm going to leave that for the next video. I'll see you in that one. Bye.